Hi, this is an example problem from Chapter 14 on the kinetic theory of gases. Pause for a moment and read the question. So we have a cylinder of helium gas at 20 degrees Celsius. There's 8 grams of it. Helium's a monatomic gas, which means that it's just a single atom. And we're told this behaves like an ideal gas, which means that the kinetic theory is valid here. Now, in part A, we're going to try to figure out what is the average kinetic energy per molecule, per helium atom in the gas. Let's recall a couple important ideas about kinetic theory. So the idea here is that the energy in the gas is really just due to the motion of the atoms as they travel around in the gas. The average kinetic energy of an atom in the gas, you can use the standard 1/2 mv squared formula if you use the mass of a helium atom and you use the average speed of the atoms, which is VRMS. Or we also know that the temperature is also a measure of the average energy of the atoms. And so we could use 3/2 kBT as well. So let's write down this important equation. All right, so for part A, we're going to calculate that average kinetic energy. And since we know what the temperature is, and we've been given Boltzmann's constant K, we'll use that version there, 3/2 kT. Now, just like with the ideal gas law, anytime you're using a temperature with kinetic theory, any of these equations, you have to use absolute temperature, Kelvin. We can tell that because Boltzmann's constant, for example, is given in joules per Kelvin. And so if we want to convert 20 degrees Celsius to Kelvin, we need to add 273, which is going to give us 293 Kelvin. That's the temperature of the gas. And we're going to end up with a certain amount of joules. Let's see what we get. Comes out to 6.07 times 10 to the minus 21st joules. Now it's a very small number because we're talking about an atom, which is a very small thing. Let's look at part B. Calculate the internal energy of the system. So internal energy is U. It's the energy due to the internal motion of the gas. In other words, it's the energy of the atoms that are moving around, the sum of all the atoms, their energy. Now if we go down for a second here, we can look at internal energy. And it's pretty easy actually. If you know the average kinetic energy, the total internal energy of the gas is just the sum of all the kinetic energy. So if you know the average value of it, you just multiply times n, the number of particles, or helium atoms in this case, in the gas. You can also do it, if you want to use this equation here, 3/2 n kBT, and of course you saw that we just did 3/2 kBT originally. So we need to figure out what n is and then multiply by the average value of Ke. So in this case, let's try to figure out how many particles there are. I know that there's 4 grams per mole, and I can use the Avogadro's number to convert from moles to numbers of particles. So let's go ahead and do that. Before we go ahead and calculate U, we're going to say, all right, I've got 8 grams of helium. Let's convert that to moles. So there's 4.00 grams of helium per 1 mole. And using Avogadro's number, we know that for 1 mole, we've got 6.02 times 10 to the 23rd particles, or in this case atoms, of helium. So this is going to give us the number of particles that we have. And in fact, we call this n, the number of particles. So why don't we go ahead and just write that down over here. So that's 2 moles of helium, which is 1.204 times 10 to 24th helium atoms. Now we can go ahead and figure out what the internal energy is here. So to calculate U, we just take the number of atoms times the average kinetic energy, and we'll get the answer here. So 1.204 times 10 to the 24th multiplied by the average kinetic energy for each atom. Whoops, that's a 1. And that gives us a value of 7.3 times 10 to the third joules of internal energy for the gas. Finally, part C, calculate the RMS speed of the gas molecules. We can actually do it just by solving for the RMS speed with any of these equations if we want. I'm going to go ahead and do it with the 3/2 kT, right? So for part C, if we say we have 1/2 mass of the particle, that's the mass of helium, the RMS squared we're looking for, equal to 3/2 kT. Well, we can multiply by 2 on both sides, cancel the halves out, and let's solve for VRMS. So V RMS squared is equal to, got to divide by MP, so I'm going to get a K, sorry, there's a 3, a K, a T, divided by the mass of the particle. And then to remove the square root, I'm going to go do this. And so we end up with this. VRMS is equal to the square root of 3 kT over the mass of the particle. Now again, we need to be in absolute temperature. So Boltzmann's constant, 1.38 times 10 minus 23rd joules per Kelvin. Temperature, 293 Kelvin. The mass of the particle is given to us above, 6.646 times 10 to the minus 27. And I need to be kilograms here because I've got joules above. Remember that if I cancel out the Kelvin and I've got a square root of a joule divided by a kilogram, remember that a joule is a kilogram meter squared per second squared, so the kilograms cancel, and then we take the square root of meter squared second squared, so we're going to get a speed as we should. Putting this into the calculator, we get a speed of 1,350 meters per second. That's our VRMS speed. That's the average speed of the helium atoms as they're moving around inside that cylinder.